Almost there, folks. Any questions at the moment? I think it's official. Welcome back, everyone. We're in a special time of the semester. It's midterms week, so I hope it's not going too rough for anyone. Also, good news is when we come back, it'll be March and we'll be thinking about daylight savings time, so that's kind of cool. Other things to mention, though, is that I did forget to write a quiz, so there's none due today, but we do have a new one that's posted. This one will be due next Wednesday. Don't have a lot of other announcements, but any questions or comments at the moment, folks? Okay, we're going to finish off section 3.5 today, so the due date will be a week away. And we'll start our next section, 3.6. This will be considered one of our bigger application sections. We're going to take another look at exponential growth, exponential decay, but now from a more calculus kind of side of things. So this will be kind of a nice section to see calculus and chain rule put into action. And aside from that, with what we've got going on in the future, next week is a pretty normal week. So we'll just do more problems as normal. But then the week thereafter will be our second exam week. That means pretty shortly I'm going to start adding more information here, the review problems and such that you would expect. But we'll talk a little bit more about that exam as we get closer and closer to it. For the moment, we're now back to section 3.5. So let's take a look. We're dealing with the chain rule, and there's our really fast formula for that process. We're about to do part D, which is actually kind of a nasty looking one. So let's do a really quick review or refresher kind of problem, even before that one. I think that's a good way to start off the day. Just seems sort of rude to do one of the nastier ones as our very first problem. Let's call this one a warm-up. And let's say you want to differentiate this function. Y equals 1 over e to the 5x. Now, differentiating this function, it looks alarmingly not nice. It's a fraction, so we might think quotient rule, but there's always a great trick with this. It's not actually the quotient rule unless there's a variable here and you just cannot do anything to simplify, cancel, factor, and so on. So the way we can sidestep the need for the quotient rule is to rewrite y as, actually, let's keep that in black, y equals, we want to bump this into the numerator. It's much like handling 1 over x squared. You want to put x squared up at top to make it x power -2. This one will have a base e, which goes to the numerator. And now the new exponent is -5x. This is the hard one to differentiate. And if you do that one algebraic step, you've cut the work, I'd say essentially in half, at least the amount of writing that you'd have to do to calculate it. So always try to point out those algebraic maneuvers that make life a lot easier with calculus. But now that we've done that, it's still a chain rule. So we have to think in terms of inner function, outer function. And this right here is the inner function that will differentiate second. And the base e exponential, that's the outer function. It looks kind of weird because I'm just pointing to the letter e. But if you want to think of it as the outer function, think of it as, say, e to the x really, and the -5x is what went into that position. So that's our chain rule setup so far. Let's also color code these. And when we go to differentiate, call it either y prime or dy dx, your preference. The very first thing to differentiate is that right there. But we know the derivative of e to the x is e to the x. The thing that's kind of challenging is the algebraic format. It's that, but we put in a parenthesis where x was. So derivative of the base exponential turns into e to a power, these parentheses will be temporary, multiplied by the derivative of something. That's something like before. And again, matching what this is trying to say with the arrows is you copy something inside here, but exactly in its format of -5x. Let me shade that a little bit better. The negative is included there. Then when you copy it to the second position, there should be a derivative symbol. There it is, r prime. And we'll differentiate it at that step there. At this stage, we've gone through the chain rule. All we have to do is now just finish off the derivative. Over here, nothing's going to change. The derivative of this one turns into a -5. I like to put my constants -5 out front, so that's a very stylistic choice. You don't have to do so. But if you kept the e -5x as your first term, you'd have to put parentheses around it, so you're not indicating subtracting by 5. That's one of the reasons why putting your constants out front, especially if there's a negative sign, this makes it read a little bit better. Then nothing's happening here. We'll just throw it in without the parentheses, e to the power of -5x. So we did it, folks. That's our derivative of this thing right here. Any questions on getting through that warm-up question? Okay, well, that was so fun. Let's try it again. Now we'll take on part D. This one was meant to be, again, kind of one of the more challenging ones that you'll see in WebAssign. The upcoming quiz and exam questions, they're a little bit more routine. Something more like this, for example, on the warm-up question. But this is definitely good practice for calculus because sometimes computations, they just get long. We'll be faced with dealing with that back to chapter 4. So this helps us out practicing right now. Now, taking the derivative of this thing has the same feature. There is an inner function. It's that rational function on the inside. So this will be inner. The outer function is the power 6 function. So if we were to color code these in the same way, we'll do green for the inner function, blue for the outer function, and here's how the derivative starts. H prime of t will be first, following the color coding and the steps we wrote out, differentiate the power 6 function. Power rule says 6 becomes a coefficient, and the new power is down by 1, so a power 5. But then we have to multiply by the derivative of that thing. So we'll go like this. Differentiate t squared minus 3, t squared plus 3. And that one's the quotient rule. There's nothing we can do about it. There's no simplification. Factoring doesn't help. We'll just have to live with life on this one. And over here, it copies in. Not as bad because it's just copying in and all set. T squared minus 3. T squared plus 3. So that's how the process starts so far. Now we just have to crank out the derivative, simplify it as much as possible. Any questions, folks, on the format for it starting out? Okay, now when you observe, you're about to do a quotient rule, and there's a bunch of stuff right here that you have to deal with. You don't necessarily want to copy this down every single step that you take. I mean, your hand will get tired after a while. So sometimes the better strategy is, let's just differentiate that part first. Let's focus on this location. We'll find the derivative of that portion, use the quotient rule, and then we'll just plug it back into the function and simplify the whole thing. We'll probably need a new page as well, so let's drop it down here. So focusing on this location, here's how we're going to start. The derivative of that thing, I'll write it out again just to show what we're about to calculate. T squared minus 3, t squared plus 3, prime, will turn into this. I'll write it out with an additional step, but if the first thing you put down was the derivative of the numerator, 2t, that's a good thing to do. That's kind of what our goal is in understanding the chain rule. But for the sake of practicing, here's how it's a good way to write it out. Bring in the top function, t squared minus 3, and put a prime symbol on to differentiate. Go to the bottom function and copy it in, multiplying. So parenthesis t squared plus 3. Then if you're like me, extend your fraction bar a little bit further, put in a negative sign and copy in the numerator. Definitely needs parentheses because it's 2 terms. T squared plus, and let's copy that in right. T squared minus 3 goes in. Then for the denominator, t squared plus 3. And a prime to remind us we're differentiating that one. The denominator is t squared plus 3, and then to the power of 2. So there's our quotient rule. We'll crank this out, simplify it, plug it back here in purple, and then we'll simplify h prime of t. Well, any questions, folks, on the format at the moment? The derivatives are not too bad. Because it's a constant -3, that goes to a 0, so does the +3. So this derivative will turn into a 2t right here, multiplying t squared plus 3. All the way to here, I'm just copying, so minus t squared minus 3. Then a new derivative, this one will turn this into a 2t as well. And the whole thing divide by t squared plus 3 squared. So we're on our way. We need to distribute 2, 3 into these groups, combine our like terms, and we should have it fully simplified. So first, here's the distribution phase. If 2t distributes in, we get 2t cubed plus 6t. On this distribution, I'm going to do it double-sided, so let me use some arrows. First, I would distribute this in and this in. Effectively, you're just multiplying by -2t, but it's sometimes helpful to visualize it this way. This will turn into -2t cubed. Then distribute again. The negative sign multiplies that, makes it a +3. At the other end, 2t multiplies it, and now we have plus 6t. So here's our plus 6t for that distribution. T squared plus 3 squared still in the denominator. And here's our reward for all that hard work. The 2t cubed and the -2t cubed cancel off, so those are gone. 6t and 6t add together as like terms. So finally, altogether, the quotient rule results in 12t divided by t squared plus 3 squared. Well, we did it, folks. We did one part of that problem, which was the quotient rule right there. Any questions at all to this stage? Okay, now let's plug everything back. And just to show how the substitution works, I'll use this, well, boxes are kind of weird. It makes it look like that's the answer. That's just a weird thing that we get used to as math students, I'd say. I'll just use a line. So this portion here connects to that, and that's what we're going to substitute in. So h prime of t equals, I'll go to black on things we're just copying in. There'll be 6 times, and simplifying on this one is a little bit non-standard. You actually want to raise the numerator to the 5th power. So t squared minus 3 to 5th power, and raise the denominator to the 5th power. It'll make sense why we want to do this in just a moment. T squared plus 3 to the 5th power. So I've raised numerator here, denominator to the 5th power. Now here's the exciting step. We take this portion, which was this location, taking that derivative, we have times 12t divided by t squared plus 3 power 2. With a purple Y just to say that connected from here to here to here, and now it got dropped into that location. Now we're just about done. We'll take 6 times 12 to get a 72. T times t squared minus 3 to the 5th power. But then down below, this is the reason we raised numerator, denominator to 5th power. These are like bases. The easiest way to simplify is now to combine them. It's to power 7, adding up the powers. So t squared plus 3 to the 7th power. And we got it, folks. That's our derivative using chain rule, quotient rule, and a bunch of other stuff right here as well. These are really long problems, but it's good practice to get used to these kinds of things because sometimes it's just part of life with a calculus problem. We'll see things that get kind of hairy like this in chapter 4 here and there. Any questions or comments, folks, on the conclusion to this one? Okay, well, we've pretty much done it. That's getting through the chain rule. I have a couple other concept questions to take a look at. One of them is going to be doing another tangent line computation. And the next one is a pretty honest application. So let's take a look at those next. You know what, and I forgot about this one. There's an extra formula, and then we'll take a look at those other ones next. It turns out the reason this formula has only appeared today in section 3.5 is that to derive this formula, you actually need the chain rule. It's something else called implicit differentiation. But there's another rule that we used along these lines. It went like this. The derivative with respect to x of e to the power of x is itself e to the power of x. This is if you're using a base e exponential. That is a very unique exponential function. It doesn't work like this for any other one. So if you did have a different exponential function, say it's to the base b, well, now that's a generic one. We're going to assume b is positive and it's not equal to positive 1. The derivative actually goes like this. B to the power of x. The b to the power of x matches up in this location, so that's kind of comforting. But the new thing is this right here, multiplying natural logarithm of b. Why did we never have to do that here? In a certain sense, we kind of did. If we use this formula again, the base e exponential, here's what it looks like. Derivative with respect to x of e to the power of x. Now, thinking in these terms would be e to the power of x multiplied by the natural log of the base e. The natural log of base e turns into exactly 1. It's kind of a nice feature of the exponential, or excuse me, logarithmic functions. The natural logarithm function and the base e exponential are inverse to each other. So that's a cancellation, and it turns into just e to the x. That's how this formula right above here was actually working. It's through this. Well, any questions, folks, with that formula down below? Okay, for a related example, here's a really fast one. Let's say you had a function y equals, just say 5 to the power of x. Nothing too major. There's no chain rule here, just a normal derivative. This could even be a real exam 2 question, so something to be prepared for. Then the derivative, let's call this one dy dx. Through the formula, it would first be 5 to the power of x, reminding us how the other exponential function worked. But when you notice that base is not base e, you really have to write out this part. Natural log of 5 is how it would come in. Then that's the correct derivative here on that really fast example. That looks kind of funny though. Let me make that more obviously look like an n for natural log. So that's how those derivatives work. But now that you have this extra formula right here, there's actually some confusion. These functions are all very different processes in differentiating. So the purpose of example 3 is to see what happens as we change the format of the functions, how the differentiation process itself will change. But first, any questions at all at the moment? Okay, let's first differentiate this one to start. Y equals x cubed. Then I'll just call these y primes. This one's not too bad. We just use the power rule. But the reason we use the power rule is the thing that varies, x itself, is a base this time. So all we have to do is write 3 x squared. In other words, the reason this is a nice derivative is because this one is a power function. We have x to a power, in other words. If you change that, then the process will change as well. Notice how tricky that is. Y equals x cubed versus y equals 3 to the x. That's almost kind of like a trick on our mind, right? We have to know that there was a substantial change here. If you have y equals 3 to the power of x, this is not a power function. This is referred to as an exponential function. So just like the one in purple where we did the warm-up, derivative of 3 to the power of x, now that we recognize its right form, we use that formula. It becomes y prime equals 3 to the power of x multiplied by natural log 3. Really not too bad once we know which formula we're using and how it should go. So that's 2 derivatives down. The one on the left and the one on the right are the ones that are very, very easy to conflate. So these are 2 good examples to keep in mind. That leaves the last one. Now this one is still an exponential function because we have a base 9, and in the power position is something that depends on x. But because there's more than just x there, this one's also a chain rule at the same time. So let's handle this one extra careful. So y equals 9. Because it's a power, it actually does matter how we write these down. We have to write the 3 minus 5x squared, so it truly appears as an exponent. I'm not picky about that, but if you wrote it this way, then that's when we would definitely have a problem. It's not clear what function we're even really looking at that point. So try to get your typesetting or handwriting to get a little bit raised here so it's more obviously an exponent. At that stage, we have an inner function. It's this one right here, 3 minus 5x squared. So there's our inner one. The base 9 exponential, that's going to be our outer function. And so that tells us how we ought to differentiate this. Like before, we can put that in green, this one in blue. That's usually how I'll try to color code the chain rules, and at least in this section. Try to do it for the rest of them. And y prime now becomes, first, we have the derivative of this one. It definitely looks weird because we've never done a chain rule with the base 9 exponential, base 5 exponential, and so on. We've only done it with these exponentials. So here's the brand new feature. We would write 9 to a power like before. Parentheses are optional, but it helps organize what goes where. Then you have to write down immediately after, just so we don't forget, natural log 9. Then multiply by the derivative of something. So this is how the chain rule starts on this. The portion in blue is referring to the outer derivative using this formula. With the placeholders, we just put in the inner function, 3 minus 5x squared. They'll go here and here. We still haven't calculated it, but seeing how the chain rule goes together is usually a lot more than half the battle, so we're just about there. Any questions or comments, folks, on how this came together? Okay, let's see how this finishes off then. Everything here is just going to be copied. I'm going to calculate this derivative, but I'm going to put it out front so I don't accidentally conflate something being subtracted when it's truly multiplying. So we get for our derivative, y prime equals, the derivative of this will have a 0. Here we'll get a negative 10x. Then everything else is completely copied down. I'd usually put the natural log a little bit or put it up front as well, just to be careful. That's, again, a stylistic choice. You could leave it to the right if you prefer. Then copy in this portion times 9 to the power of 3 minus 5x squared. You can drop the parentheses there if you'd like. That's, again, just another stylistic choice. Parentheses here were more for organization. And that's the final answer. There's no simplification we can do, so we just leave it in that kind of format. I think those are, again, some pretty tricky derivatives, so this is a good one to come back to. Any questions, folks, with running down those three? Okay, riveting stuff. So now we've got a lot more derivatives we can take. This is going to be useful for us, the chain rule, these extra exponential functions, when we go into content about exponential growth, exponential decay. But before we do that, let's practice some more just for the sake of practice. I believe there's a question like this in the homework, so we ought to do one more like this one as well. Then, if folks would like, we can turn to the application, but let's park it here for the moment. Okay, so it says this could be definitely an exam question or a quiz question. Find the tangent line to this curve at the point 1, 1. Because it says find the tangent line, we're going for the full equation to this thing. First thing we have to do is differentiate the function. But even before you differentiate it, you have to consider what algebraic format is this actually in. Sometimes we would correct this, write that root as a power 1/2 and run through it. But that process is extremely common. Square roots are used all the time. In a plane, they're used for distances. So you see a lot of square roots when you optimize in chapter 4. And because it's so common, let's write down our formula for square root. It's a shortcut you could use if you like, but you don't have to. So if you're going to differentiate any square root, say y equals root x, the process that we take is we like to write it this way. y equals x to the power of 1/2. Then we just use the power rule on that thing. We can say dy dx equals, first thing that will happen is power 1/2 is a coefficient now. The base x stays in the same position in the numerator, but we subtract 2/2 from that to get a negative 1/2. And then that's a completely acceptable answer. But if you wanted to make a formula, not a bad idea to make that exponent positive now. You'd be chucking it down into the denominator, so it gets demoted to look like this. 1/2 to x, 2 times x to the power of 1/2. Now, the next thing you could say is, it is completely fine in this stage, but if the problem starts with the root x, it's sometimes just visually pleasing to end in the same format, using square root notation again. So back over here, you could say this is 1/2 square root of x. And again, this process is so familiar that you might decide, I don't want to do this every single time and reinvent the wheel. Instead, you could just say as an overall punchline, maybe put it over here, the derivative with respect to x, this only works for the square root of x, not the cube root, not the fourth root, the format would change. But if it's square root of x, each and every single time, you just get 1/2 root x. It's a pretty fast formula. It's not necessary or required, but it does increase quality of life when you're differentiating these kinds of things so often. Well, any questions, folks, about the formula here? Okay, it is an optional formula, so if you don't like it, good news is you don't actually have to use it. Let's actually use it on this thing and just see how it goes. Let me rewrite y so we can just visualize it better. It's the square root of 9x minus 8. That is a chain rule problem where the 9x minus 8 is the inner function. And now the whole square root symbol, I'll just point to that portion of the radical symbol, that is the outer function. That's going to be kind of difficult to highlight, but let's make this happen. So here's the inner function in green. The outer function is this one. And we have a format for that derivative. So we can calculate the derivative immediately and say y prime equals derivative of outer function always comes out in this format. So it's 1/2 square root. I want to leave it blank because something other than x goes inside there. The inner function is going in that location. Then you multiply by the derivative of that inner function. But let me keep my color codings consistent. We usually put this one in green. So this is the setup. We've taken care of the outer function derivative. We used that format right there. But instead of x, we just blew a hole right there where the square root is. Now throw in 9x minus 8 in that location and that location. At that stage, the derivative is just about done. No further work whatsoever for that denominator. And when we finish this derivative, because it's multiplying, we're just going to chuck it into the numerator right here. So the whole thing is, first copy denominator, 2 root 9x minus 8. Then we took the derivative of 9x minus 8. That comes out as a 9. We put that in green because that is a new derivative we took from right here. And that's where it ends. That's the complete derivative. No worries about changing the exponents on this thing. You can just directly use this formula to come down there if you'd like. Any questions at all, folks, to that stage? Okay, well, because it's saying find the equation of the tangent line, this is definitely not the whole problem. On step 2, we need the slope m. That's so important, I think it deserves a note color. Let's go with indigo. M is going to be found by taking, kind of regret calling it y prime. The downside with using y prime is we don't have a great way to indicate function notation for that thing. So if you wanted to, you could call this also dy dx. Leibniz notation is a little bit more advantageous if this is what you're about to do next. you're going to plug a value inside the derivative, whether it's dy dx or y prime, if you want to indicate the value well, then you'd be using this value. Here's your x1. This is your y1, and m would be dy dx. That vertical bar now says evaluate dy dx at x equals 1. So take the first coordinate right here. This is how we express we're throwing 1 inside a y prime. It's pretty ugly, but it's worth understanding, visually looking at it, training your eyes to get used to it, because it's also common. That's kind of tragic. Some notation that looks terrible is common notation. So x equals 1 just goes right there. We just simplify that whole thing down. So this will be equal to 9 divided by square 2 times the square root of 9 times 1 minus 8. From here, we're just numerically simplifying this. We want it simplified as possible because we're going to have to work with that thing. We don't want the slope in that format. It's clunky to write. So above it, we have 9. 2 times the square root. This is just 9 minus 8 for square root of 1. Square root of 1 is still a 1, so this comes out as 9 halves. Let me change the color coding on this. Let's call this x1, y1 rather, in black. Okay, so that's our step 2. We've got the slope of the tangent line. If this was an exam question and you got this far, let's say it's a 10-point question, I'd probably consider this either 8 or 9 of the 10 points because this is the punchline. The derivative itself gave you that slope. The third thing is more just finalizing it. This is the algebra review portion. So step 3, I'll use this formula, y minus y1 is slope m times x minus x1. But now we're just dropping in 3 different values. So 3 different substitutions, and we'll finish off the problem. So our x1, y1 are provided above. So we'll get y minus 1 for the y1 equals the slope n, which is 9 halves, times x minus x1, first coordinate. And that's our tangent line equation. Well, the side wants us to solve this for y, and that's a good idea. You can check your work pretty rapidly if you did that. So let's take and write this as y minus 2 over 2 is instead of 1. Distribute the 9 halves through to get 9 halves of x minus 9 halves. And last bit to scroll, I think we're going to fit this one. Add 2 over 2 to both sides, and the tangent line equation is y is 9 halves x minus 7 halves. So my claim is that's the right equation. Is it? I have no idea. We have to ensure that there was not a single mistake, calculus, algebraic, arithmetic, or otherwise in any of these steps. I mean, it's a lot of steps. So if you do this as a homework problem or a quiz problem, you definitely would want to check it out. We've done this before, but here's the reminder. It's a worthy thing to do. Start by putting in your function, y equals square root 9x minus 8. It's a good idea to get the domain configured right, or the picture will look weird. We need to be around positive 1, and so, I think our picture we have here is okay. We have 1 in this location. Next thing we throw in is the tangent line equation. So y equals 9 halves x. That already looks concerning. There we go, looks better. That already still looks concerning. Let's subtract 7 halves. And, well, let's see if that looks right. Here's 1, 1. So if I zoom in on that spot, the tangent line and the red line should start to become equivalent to each other. Let's take a look. This is our check. This is looking very much like a tangent line to this level of zoom already. If anything was just a tiny bit off, say plus 0.002, you'll probably be able to detect that by zooming in. The lines actually start to separate by even a tiny amount of error right there. Fix it and they'll start to look equivalent. Well, that's the process, folks. Any questions at all in getting through that or looking at the check? Okay, well, the chain rule is an adventure. When you learn it in section 3.5, That's kind of just our introduction to chain rule. It's something that's going to start to come up in all of the other sections throughout the course, so we'll be practicing it quite a lot. But where we need to practice the chain rule the most is, in fact, this kind of question right here. Just like we looked at on the other problems, sometimes there feels like there's a big disconnect between the way calculus looks like in a math setting versus an applied setting, because in an applied setting, they're not going to use X's and Y's. We use symbolisms and formulas that capture the nature of the problem, like S, C, R, and lowercase r. But this one's a worthy problem. This one looks like it's about possibly pharmacy or about human biology. It says the speed. Already that's a derivative if they say speed. That's a rate of change, distance over time. So here we have something that's like a velocity in a certain sense. The speed of blood, that is our centimeters from the center of an artery, is given by that equation. So depending on how far your blood platelet is away from the center, it affects the speed because of the flow dynamics somehow with human blood and veins. So we want to track how that speed changes based upon what exactly? Who knows? There's a lot of variables here. So the speed of blood depends on how far you are away from the center in r centimeters. It's given by this formula where that's wonderful information. If you find a constant, we should definitely recall that. We have a constant here. So when we differentiate, we'll use the fact that that's constant. Here, r is the radius of the artery. And I believe that's the variable. Your arteries can constrict or expand depending on different metabolism things happening. And we're wondering, how is that going to affect the speed of the blood if the artery itself constricts? So we're wondering what happens with that radius. Let's put that in blue because that starts to look like the variable. S is measured in centimeters per second. That's good information, but it's more just giving us the unit. Let's recall it just by highlighting it maybe. But nothing major. Let's go for a gray on that one. So that's a setting so far. This one looks like it is pharmacokinetics because they say, suppose a drug is administered and the artery begins to dilate. I believe that means get wider if they say dilate at a rate of dr dt. They don't tell us the rate, but they're indicating r is a function of time if they say dr dt. That's something we need to recall, so that might be a good note to make right here. Because they said dr dt, we now need to say r is a function of time, which makes sense. We're talking about the time after a drug was administered. So whatever that drug was, imagine some kind of steroid. Well, I'm not sure if that would dilate anything, but imagine some kind of drug causing a dilation. The amount of dilation would depend on time after the drug was injected. So we have that information there. It says at a constant distance r. Now, the way they initialized that is very special because they didn't say it exactly like c is a constant, but they are indicating little case r is constant in this problem. So the thing that we're tracking is the dilation of r, it getting bigger. We're leaving r fixed. So right here, that's our second constant. That will tremendously help us differentiate. Finally, here's the question. Find the rate at which s changes with respect to time. So they're asking us to calculate ds dt, just by that statement right there. I suspect that's probably a good one to highlight as well. Don't want to try to highlight the whole problem, but it's good to know when the actual question was indicated. This right here is asking for a derivative. It's asking for a specific one. So Leibniz really helps us nail down the form of that derivative just right. So we want to know how fast is the speed going to change as the radius of this gets larger. That stays exactly where it is, where the constant c must have been given us from some biology students. We'll use that specific value for r. And the only thing we know about this function right here is dr dt is 10 to the power negative 5. So that's the rate at which this thing is changing. It's getting bigger because this is a positive quantity, but by a very, very minute amount. I mean, it is a blood vessel. It takes a while to read through these kinds of things, but when you see these kinds of problems, that's a good strategy. I would probably read through it a few times. Make sure we didn't miss anything subtle, like the fact that this right here was indicating a constant as well. And this is the actual variable of the problem. Well, we know we need to calculate this. At some time t naught, and that time t naught will be when all of this occurs. At time t equals t naught. One thing they didn't tell us is the time that actually will happen, but we'll still use all this information to show what this comes out as. In other words, we're going to differentiate that function. If you're differentiating that, a good idea is reformat it in a way that's just easier to differentiate. There's no reason the constant has to be there, except maybe that's how the function came together when they were deriving it. Let's distribute it through to get CR squared minus, let me fix that exponent first, minus C times lowercase r squared. All of this, they told us is a constant. So good news, if you differentiate that, it's just gone. It's just eliminated from the problem. This portion right here is also constant. And that portion is the variable. Differentiating this is really tricky. Let me show you why. This r is a function of time. There's a legitimate function inside there. That means r is the inner function. This is not just your ordinary variable. It's really something like this. R equals r of t, some other function of time itself. Then up here, the power 2 function. This one is the outer function. We'll handle second, or excuse me, handle first, and then differentiate the inner function second. But to me, that's what makes doing calculus in applied settings in the sciences, where it's massively important, it's also pretty confusing because we have to get used to these kinds of ways of indicating variables and whole entire functions as well. Well, any questions, folks, to this stage of the analysis? Okay, what we need to do next is actually differentiate that thing. So here's where we'll put down ds dt. We need to very carefully differentiate this. The first rule we'll use is the constant multiple rule. That's a constant multiplying. It's much like a 5 times x. So upon differentiating, no change. We just throw in that constant again. Here's where we're going to be really careful. And I notice my color coding is a little bit backwards. Well, let's keep it in this order so we don't have to rewrite everything. We'll differentiate the outer function, and it looks like this to start. Times 2, something to a power of 1. I'm going to drop that power of 1, but I'm just tracking the change on that derivative, showing how it goes. Then you multiply by a derivative of something. I'll write out this way, which is how we typically wrote it. However, we would usually write this one in blue. Then take whatever your inner function was, it's this function right here, r, goes in that location where it's a power 1, and it goes in this location where it's differentiated. Differentiated with respect to what variable? It had to have been t. That's the derivative we're taking here, ds dt. So we're going to clarify this one and call it dr dt. That's what we're really looking at when we look at r prime. So on our next step, let's simplify this down and call this 2 times c times r times, that location is dr dt. And let's fix that r. I mean, that is a r, but it should be an uppercase r. R's have different meaning depending on the case. There we go. That's our derivative. The only thing we haven't done is now plugged in these quantities that occur at some specific time t naught. So we're finally getting to that last stage, cranking out that actual rate of change. Well, any questions, folks, at the moment? Okay, it's really easy to lose track of what we're trying to calculate when the computations get long, but here's the idea. R is getting bigger, so your whole vein is widening. This is staying in a fixed position, and what we're wondering is, what is the rate of change of the speed here? Will it begin going faster, or will it begin going slower? Well, it just depends on how all these constants combine. They're all positive constants, so this will be constant, and that means if this starts to dilate, this is going to move faster. Let's take a look and start to crank out these values. So last step, let's move down to ds dt. Now it's evaluated at some time t naught, where all of these constants are in effect. C was a constant the whole time, so it always had this value right here. Let's plug it in for the 2 times this constant, 1.76 times 10 to the power of 5. So that takes care of 2 times c. We need the value of r, and they're only wondering about the speed when it dilates to that amount or that length. So 1.2 times 10 to the power of -2. So that takes care of the value of r. Next, dr dt. We're only interested when it's dilating at a specific rate as well. That's when it's moving at this rate, 10 to the power of -5. So we've got all the constants in, but the bigger challenge to this is, what is the actual unit? S was measured in centimeters per second to start. That's the unit of this numerator, so we can say centimeters per second, but then we're taking a derivative with respect to time. So this is centimeters per second. And that's such an awkward unit. It is the right unit that it does in fact get simplified. We'll do that on the next step. So centimeters per second is a kind of acceleration. And the way the units go is we take centimeters per second, we multiply by the reciprocal of this, 1 over second, and we get centimeters per second squared is how we officially write a unit like that. If we differentiate again, it'd be centimeters per second cubed and so on and so forth. So that's how it all comes together. Last thing to do is to throw this into a calculator, but I sincerely felt that putting this in a calculator was probably not the most riveting material. So I pre-calculated this. All these constants multiply together, and it came out to 4.224 times 10 to the power of -2 centimeters per second squared. So that figure right there is the acceleration of a piece of blood, a fixed distance r away from the center. When r extends out to that distance, increases at that rate, and this constant takes on that value, wherever they got that constant. Kind of a weird process, but any questions at all, folks, on getting through it? Okay, well, just to be completely honest, I do not have one like this in the actual homework assignment. The reason we're doing these towards the end of class is, well, twofold. It's interesting to see how calculus connects with anything in real life, any kind of real application. And also, we're going to be going for these kinds of applications in chapter 4. The hardest part is knowing how to differentiate these kinds of things. So we're practicing now, so we're not just kind of thrown against a wall in chapter 4. But we did it, folks. This is the end of the chain rule. We'll be going next to section 3.6, exponential growth, exponential decay. Any questions whatsoever before we turn the page to the next section? Okay, let's take a look at those. Looking at the time, we have about 25 minutes altogether. I think that'll be enough time to make some headway describing the process we're about to take a look at and get through most of the second example. So we'll make some decent headway to start through this. First thing we have to look at is how does this all go together? And how does calculus connect with exponential growth and decay? For me as a student, that was always kind of a weird question because in an algebra class, you're simply just provided this. They don't necessarily tell you where that came from. They just say, trust us, that's the right equation for the thing you're trying to solve. What we never said was, what is the thing you're trying to solve? That's up here in the definitions. So here's how it tracks. Y of t is going to be the value of some kind of quantity at a time t. It could be a population. It could be amount of money in a bank account. It could be, say, the amount of mass of something that's decaying radioactively. So the value or quantity of something at time t is what y is. If the rate of change of y with respect to t is proportional to its size y of t at time t, that's a heck of a statement right there. Let's unpack it. The rate of change of y. What they're referring to right there when they say that is this. dy dt is what we mean when we say the rate of change of y with respect to t. And I should have highlighted a little bit better. Let me try again. Should go way out here. The rate of change of y with respect to t is dy dt. Next, they say is proportional to its size, y of t. From that statement right there, we need to write down an equation that involves proportionality. And these are usually multiplication type equations. You would take your y and multiply it by something. Let me just use that arrow so it doesn't look weird. That means the k value right here is the constant of proportionality. We typically don't say that if it's the context of growth and decay. Instead, we say k is either the relative growth rate, if it's positive, or relative decay rate. So that's a constant proportionality. And it goes right there. So what was indicated verbally is an honest differential equation. What makes it a differential equation is the fact that there's a derivative in an equation which involves an unknown function y. Our objective is to solve for that function y using information about its growth or decay, the k value there. So that's how exponential growth and decay actually starts. We pose the question, what if a population grows in a way, that's the rate of change, so that its growth is proportional to its population size? That's the differential equation folks wanted to solve. And they found the only potential solutions to that differential equation are of this format right here. And we're going to verify that. We're going to show that's the right solution to that differential equation, but we're also going to break it down and see how it connects with a specific example to make it less abstract. So this right here is the solution to the differential equation dy dt equals ky. So kind of weird in a sense. Equations are funny in the sense that usually when you say equation, you're trying to find a value for x that satisfies the equation. It's the same thing in spirit here, but what you're looking for is an entire function, not a number, an entire function that would satisfy this property. The derivative of that function is a number multiplying itself. Kind of weird in a way. Any questions so far, folks, about the differential equation or the solution down below? Okay, well, let's take another look at this function right here. We're going to change y of t to something specific. We put down p, we're thinking about population size. We put down m, we're thinking about mass, and so on. And so it says here, p of t describes the population size of a country. Who knows what country, just a random example, at time t measured in years. It asks us which portion of the function represents the relative growth rate. Probably a good time to start color coding these things. Let's use maybe green for relative growth rate. Any volunteers for say which portion is that value there?
The 750E.
Not quite. It would be something other than that. Yeah,
Would it be the point, 25, the 0.235, if I.
yeah, exactly. So that growth rate is this right here, the problem, which connects with that K right there and the K right there in the formula above. So in our problem, K is 0.235. So spotting that, I mean, this could be a real honest exam question where all I'm asking you are basic concepts about an exponential function. So you could expect this to be a real question even. It asks next, which portion of the function represents the initial population size? And you see which number would be the population size initially?
That one be 750.
Exactly, absolutely. This 750 right here is the true initial population size. Sometimes we just call it an initial value, but if it's a population we're tracking, we'll say population size. It tracks back up to this quantity. And notice there's nothing to highlight in the original differential equation at all. It's not represented there. It's represented in this location. And the way it's written out is actually pretty helpful as well, even though it looks funny. So if you see a y of 0, but your function is a p function, just write out p of 0. Where are you putting the 0? It's going right here where t is. So it becomes 750 times the base e exponential to the power of 0.235. But t is the input right here. We plugged in 0. So 0 goes into that location. This whole thing is now e to the power of 0, which means it equals 750 times 1. Since e to the power of 0 is 1 itself, that's how we get a size of 750 initially. So notice we went through this just because it's practice, really, but it was looking at us the whole time. So this is a very valid shortcut if you think in those terms. That is the initial population size. So those are the two major things we'd want to track whenever we're dealing with an exponential function. We need the growth rate or decay rate, that's the K value, and we need an initial size, that's the P of 0 or P naught value. Well, any questions so far, folks, at the moment? Okay, now when it says this right here, we're doing something completely new. We're trying to show that that function above, P of t, really solves that differential equation down below. Let's take another look at that equation. It's the same as the one above. This one said dy dt. We'll say dp dt, since we're dealing with the population. It said ky here, but it now has to say k times p on the right-hand side. So we're trying to show that this is a solution to that. How do we check it? Well, just like any solution you're trying to verify, suppose it's like 2x plus 5 equals 10, you'd plug in the supposed solution for x, but here, we're plugging in this supposed solution for dp dt and seeing if the derivative really comes out as k times p. So first thing we have to do, and really the first and only thing, is begin with the left-hand side, dp dt. We're going to take a bunch of calculus steps and show that it equals the right-hand side, k times p. But this is the function we're differentiating, so here's how it goes. d dt, I'm going to insert the function 750 e to the power of 0.235t. And the color coding is actually pretty important on this one to see. You don't have to do it for your notes, but I'll try to be careful on paper here. Or this is not exactly paper, but you know what I mean. So when we're trying to track this, we're trying to get the value of k to emerge right here. Then we're trying to get the value of p, which is that entire function, to emerge in that location. Let's maybe highlight that portion of yellow to convey it. If we can make that happen, our work is done. So back over here, it's an ordinary differentiation kind of problem. There's a constant multiplying a function. So first thing you can say is that it's equal to the constant now times the derivative of that function, e to the power 0.235 times t. A chain rule comes up right in this situation, but the nice thing is it's a base e exponential, so it's not a crazy chain rule like we saw before. We'll think of this exponential as the outer function to be handled first. 0.235t is the inner function to be handled second. And now we're about ready to navigate through the chain rule on this thing. First thing, let's copy down 750. Now in the chain rule process, let's do this one really carefully. We differentiate the base e exponential first. Here's how it looks. And because it's a base e exponential, we don't need natural log e multiplied. That's just a 1. But we do need to multiply by the derivative of now the inner function, 0.235t. They'll come in here. And down here. Well, any questions, folks, with getting through the chain rule process on this one? Okay, well, there's one last derivative to take care of, and it's this right here. But that's just a constant times a power 1 power function. You just get a 0.235. So this turns into, well, let's also take a look at our goal. Our goal is to get to k times p, and that right there is k, the initial, or excuse me, the relative growth rate. So when I differentiate this one, I'm going to put it out front as a 0.235. Now the rest of it's going to copy in, but I think a bracket is a good call this time. The rest of it is this stuff, 750 e to the power of 0.235 times t. So now the equalities here are very important because we're connecting dp dt to our goal is k times p. And we do have equalities matching up all the way to this stage. But notice right here, that is the k value. So let's substitute in k right at this stage. And finally, it's kind of tricky on the eyes, but if you inspect this visually and stare really hard at it, sometimes I really do just stare at these things to make sure my eyes aren't tricking me. That's this right here. You could just call it p of t if you wanted to. In differential equations, people just usually suppress this and call it p without the of t part. So it would be written as times p. But that means we set out what we wanted to do. The derivative of dp dt on the left turned into k times p on the right. It turns out it is true. If you differentiate this function, it will satisfy that differential equation. It doesn't matter if you call it p of t or y of t. When it says the only solutions to dy dt equals ky are these, they really mean it. That's the only way you can solve this, is by producing a class of functions that look like that. Pretty weird, but that's how differential equations go. It's an entire subject, an entire mad science. And this is what verifying a solution looks like. I would say the bigger takeaways on this are part A, part B, could be real concept questions. But I wouldn't ask part C. This is more for us to know what they mean when they say differential equation. Well, any questions at all, folks, on running through that one? Okay, well, let's put all this to practice and give example 2 a try. It doesn't give us a lot of information, and it wants an expression for the number of bacteria after t hours. Let's see if we can track through this with what we know so far. There's really 2 formulas that we have to be aware of. It's not just the solutions we need. Sometimes we need the differential equation. So I'll try to point out when the question lines up with the differential equation, because that's going to be the thing that's totally new on this problem here. But let's give this a try. It starts off by saying a bacteria culture grows at a constant relative growth rate. From that statement already, what they're telling us is that if we let p of t be equal to I was about to say population size, but we could just say this is a bacteria culture, so how about number of cells? So number of cells at time t. So that's just from, we know we have a bacteria culture, it'll grow with time t. But right here, when it says it grows, that's a rate of change at a constant relative growth rate. That implies a differential equation, and the equation is dp dt equals k times p. So from that statement there, its whole purpose was it's initialized a differential equation. But now we know that this equation has solutions p of t equals p naught e to the power of kt. And we did in fact verify that ourselves. That is the right kind of solution. So next it says the bacteria count was 600 initially. The wording here is very, very important. We're throwing buzzwords like initially because that's the initial population size. What they told us here is population at time zero, the initialization of the experiment is 600 cells in the culture. So already we can plug that in right here. We're building up our function as we go. So population size, time t is now 600 times e to the power kt. Now, if this was a real experiment, maybe you're doing something with salmonella, who knows what the bacteria culture is, you might not actually know the growth or decay rate K, and it all depends on temperature. The agar solution that you have in your Petri dish are all important factors here. So you might have to actually experiment or verify experimentally what the growth rate could be. And this is where this comes in. This does not give us our K value. That's kind of frustrating, but it gives us another equation from which you can solve for K. And by the way, this is something people can actually do. A student told me this a few years ago. You can really count the number of bacteria. They put these things under like a light tray. The Petri dish goes under, and if a photon of light from the sensor below doesn't connect with the sensor above, the assumption is a bacteria hit it, and that's a count. So these things are actually counted with pretty great accuracy. So it says right here, the bacteria count was 75,000 after 3 hours. We need to write an equation just from that information. And here's how it goes. It's a bacteria count, so we'll say population size at time. Well, I was about to put t there, but they told us the time, 3 hours. So population at time 3 hours came out to be 75,000 bacteria. That's a legitimate equation from which we can solve for the value K. Well, after we translate this statement into that equation, notice that this P of 3, that's just this left-hand side. So we're going to take that 3, plug it in for time right into that location. And what we get is 600 e to the power of K times 3. So that's where our 3 goes in the problem. Equals 75,000. Just carry in the rest of the equation. So we're getting pretty close to being able to solve this kind of thing. We're solving an exponential equation, and that's going to be the first time I believe we've done this in this course. So it might be a review for some, might be the first time you've seen it for others. But if you're going to solve an equation like this thing, probably what you also need is a calculator as well, because we need to eliminate the coefficient of 600. Let's just divide it into 75,000. So 75,000 divided by 600 gives us 125. The suspiciously nice and round number, it means it's a made-up problem, but that's because we're just trying to focus on the calculus, not get bogged down with lots of weird rounding issues. So 125 will be the right-hand side after division, and the left-hand side is e to the power of 3 times k. Now, in order to solve this equation, Any volunteers for what the next algebraic step ought to be? As a hint, what we need is properties of logarithms to really get through this. And one property we need is if we take log to any base whatsoever, we're going to pick a specific one. But if we pick log to base b of b to the power of anything, let's just say x, that will turn into x. So that's kind of our goal with this thing. The thing playing the role of x is the 3k right here. The base that we're going to use is going to be base e. And so instead of using log base b, we'll be using the natural log. It'll look like this. Let's make that a pen just to make it official. I think purple is important since this is the key step we need to solve this for k. So it'll be natural log of e to the 3 times k on the left-hand side equals the natural logarithm of 125 on the right-hand side. So on the left, through this cancellation you see right here, we're just dealing with the fact that the base b exponential and logarithm base b are inverse functions. The cancellation always works that way. And same issue right here. The natural log and the base e functions are inverse to each other, so we've canceled off the base e exponential. All that's left now is 3k equals the natural logarithm of 125. So we're essentially done now. We're just going to divide by 3. And we get that k equals natural log of 125, let me fix that fraction, 125 divided by 3. Now you can throw this into a calculator and approximate it right away, but it's usually better to leave it in this exact form. The thing we have to remember about WebAssign is they are very picky with rounding. It's actually easier to leave it written in like this, but if you did want to numerically approximate it, I would carry down 6 digits or potentially even 8 digits just to be sure we have the right amount of accuracy for WebAssign. Otherwise, they complain quite a lot. So what we've done is we went through all these instructions and showed what each one is trying to say. And now we're ready to directly tackle this question. Find an expression for the number of bacteria after T hours. It would look like this. That denotes the number of bacteria after T hours. And we found through lots of algebraic substitutions, logarithms, all sorts of weird stuff, that it equals this. 600 goes in, e to the power. Solving for k is the hardest part about this. We're just going to multiply by t right here. It'll look like t times the natural log of 125 divided by 3. So that's how we'd probably usually write it in. Well, we did it, folks. I think this one is a pretty hard one to start, but a lot of the questions at WebAssign in this section are going to line up with the things that we do on these notes. So if you see one that looks about like this, you can come back here for some advice and motivation on what the right algebraic steps should look like. But we're definitely out of time, though. We could try to do another problem, but I think this one will be a good one to come back to when we return on Monday's class. Any questions at all then, folks, on running through what we have so far? Okay, well, have a great night, folks. If you have questions over the weekend, I'll be very happy to help out. And another thing that should happen over the weekend is I'm going to start filling in this information right here. It'll either be on, say, Friday or Saturday, but I'd like to get going on it early. So if you want to start studying early, you can see what exam 2 is going to look like, the formula sheet that's going to be provided, and those kinds of things. But have a great night, folks. I'll see you all on Monday's class.